Welcome back to the Dargslan series. This is part 13, and honestly, this is the one I've been waiting to share with you. Everything we've built in earlier parts finally clicks together here. Embeddings, vector storage, retrieval, and generation, all wired into a single pipeline. By the end, you'll watch a local LLM answer a question using text pulled straight from your own files. No cloud, no guessing, just your document speaking back to you. So let's start with the name itself. RAG breaks down into 3 jobs that happen in sequence. First, we retrieve, pulling the most relevant chunks out of a vector database, usually just the top 3 matches. Then we augment, which is a fancy word for stuffing those chunks into the prompt as context. And finally, the model generates an answer grounded in what we just handed it, and crucially, it tells you when the context doesn't actually cover your question. To see why that matters, picture asking the same question to 2 systems. Ask a plain LLM about your refund policy and you'll get a hedged generic answer. 14 to 30 days, check your receipt, contact someone. Technically not wrong, but it's not your policy. Hand that same model a chunk from your actual policy doc, and suddenly it answers with the real numbers, the real conditions, the real edge cases. Same model, same prompt. The only difference is grounding. So how do we actually get there? Every RAG system, no matter how fancy it looks, follows the same 5 steps. The user asks a question, we embed that question into a vector, typically something like 768 dimensions. Then we search a vector database for the closest matching chunks, usually the top 3. We stuff those chunks into a prompt alongside the original question, and the LLM answers, grounded in what we gave it. That's the whole pattern. The next 5 slides build it, 1 step at a time, in code. Step 1. Indexing. We point Chroma at Ollama's embedding endpoint, using nomic embed text, a small fast model purpose-built for this, then loop through every text file in our docs folder. Each file gets embedded and stored in a collection called docs, keyed by filly name. You run this once per document set, or whenever your files change. That's it. Your knowledge base is now searchable by meaning, not just keywords. Now for step 2, retrieval. We hand Chroma a question, it embeds that question with the same model, and finds the K closest chunks by vector similarity. Notice the query here. How do I get my money back? Never mentions the word refund, but the top hit comes back as the refund policy. That's semantic search doing its job, matching meaning, not keywords. With our chunks in hand, step 3 is where we wrap them into a prompt the model can actually use. The template is deliberately strict. Use only this context, and if the answer isn't there, say, I don't know. That one instruction is what stops the model from drifting back into its training data and making things up. We join the chunks with a simple separator, drop them into the context slot alongside the question, and that's the augmented prompt, ready to send. And now we send that augmented prompt to the model. This is the same Ollama endpoint from part 9, nothing new to install, just a post to by APIs you could generate with Llama 3.18b. The one detail worth noticing is temperature set to 0.2. We want the model sticking close to the context we gave it, not getting creative. Stream is off so we get the full response back in one shot, ready to return. And here's the whole system in 3 lines. Retrieve pulls the top 3 chunks, builder prompt wraps them with the question, generate sends it to the model, RAG literally. The little main block at the bottom just lets you call it from the shell, Python rag.py. What is my refund policy? And you're talking to your own files. And now the payoff. Ask about returns and the model answers straight from your policy file. 30 days, unused original receipt. Ask it the meaning of life and it just says, I don't know. That's the whole point. It's grounded in what you gave it, and when the answer isn't there, it admits it instead of inventing one. That's RAG actually working. Now, one knob worth understanding, K, the number of chunks you pull back for each query. Set it too low and you'll miss the passage you needed. Set it too high and you drown the model in noise. 3 is a solid default and what we use throughout the series. Bump it to 5 or 10 when your docs are long and split across many chunks. Beyond 20, you really want a re-ranker in the mix, otherwise the LLM just gets distracted. Speaking of things that go wrong, there are a handful of traps that quietly wreck RAG quality, and Part 15 is the deep dive on fixing them. The big ones, embedding whole documents as a single vector instead of chunking, forgetting to tell the model it's allowed to say I don't know, picking a bad K, mixing English embeddings with non-English docs, and hiding the source chunk from the user. That last one matters more than people think. Showing which chunk fed the answer builds trust and surfaces bad retrievals fast. With the pitfalls in mind, here are 4 projects worth building tonight to actually feel what RAG gives you. Point it at your markdown notes and you've got a personal Google. Index every README in a repo and ask how to run the tests. Feed it a folder of email exports to find threads by topic. Or load your team wiki and stop hunting for the PTO policy. Each one is small, useful, and something you'll come back to. Let's pull it all together. RAG is 3 jobs: retrieve, augment, generate, built from 5 small functions in roughly 30 lines of Python. The single most important line lives in your prompt template. Use only the context, otherwise say I don't know. Start with k equals 3 and tune from there. And remember, you didn't build RAG today. You wired together the embeddings, VectorDB, and API you already had. Here's a cheat sheet worth keeping open in another tab. The essentials are all here. Temperature at 0.2 for accuracy, k equals 3 as your starting point, and the gotcha that always trips people up. Chroma's documents come back nested, so you need that 0 index to reach the actual top K texts. And don't forget to show the source on success. It's how you build trust in your answers and debug fast when something goes sideways. And that's 13 down, 11 to go. Next time we leave the toy text behind and tackle real documents, PDFs, scraped websites, messy mixed formats. You'll learn why chunking strategy matters more than your embedding model, how overlap saves you from cut-off context, and why metadata is the difference between a demo and something you'd actually ship. See you in Part 14.